Welcome back. So let's continue on now with new material, starting in Chapter 7. Chapter 7 is on alcohols and phenols and also thiols. At least I want to make sure that we make a brief mention of thiols, however brief, because it makes sense to talk about them in the context of alcohols. Since if you understand one, you pretty much understand the other, or at least most of it. Good, so I think we already know what the alcohol functional group is. It's an organic derivative of water. If water is H2O, then you simply replace one of the hydrogens on water with some alkyl group, some carbon group, and you'll have yourself an alcohol. Phenols are aromatic alcohols. And notice the pronunciation too. We say phenol, not phenol. But phenols are aromatic alcohols. So that means that the other group on the OH group is going to be a benzene ring or a substituted benzene ring. And phenols are special. They have some similarities to regular aliphatic or alkyl substituted alcohols and some important differences, which we'll also get to. And finally, thiols are just the sulfur analog of alcohols, or you could also consider them to be organic derivatives of hydrogen sulfide. And all of these play very prominent roles in biological systems and in biochemical pathways. I'm not certain yet to what degree we'll cover any particular biochemical pathways in detail, but you're going to find all of these species showing up in them. And so it's important to understand something about how they behave. Now, first of all, alcohols, of course, are polar. And that means that the oxygen being sp3 hybridized will wind up having a bend geometry. The oxygen is still built on a tetrahedron, just like any other sp3 hybridized atom. But what you'll find is the two bonds to hydrogen, one to carbon and one to hydrogen, will go to two of the corners of the regular tetrahedron. And at the other two corners of the tetrahedron, you'll find the two lone pairs of electrons on the oxygen. So, but basically, naming alcohols is pretty straightforward. For example, if we simply replace one of the hydrogens on cyclohexane with an OH group, well, then we'll have cyclohexanol. Pretty straightforward. Cyclohexane, cyclohexanol. It's the all ending that we use for alcohols. And of course, this compound is not chiral. There's a plane of symmetry running right through the middle of the molecule there. What about then something like 2-pentanol? Well, we would have 5 carbons, and off of the second carbon is where we'll find our OH group. So so here's our 2-pentanol. Pentane, pentanol, and then 2-pentanol to show where that OH group is attached to carbon number 2. And of course, if you look carefully, you'll see that carbon is chiral. So in principle, you'll have both R2-pentanol and S2-pentanol. Or I'm sure you can buy it as a racemic mixture as well. Your book talks about benzyl alcohol. It calls it something like phenylmethanol, and that's not wrong, but no one calls it that. Benzyl alcohol, and again, that horrible word benzyl, makes it sound like the OH group should be on the benzene ring, but that's not the case. There's a CH2 between the benzene ring and the alcohol group in benzyl alcohol. So it is one more carbon in it than phenol. In phenol, the OH group is attached directly to the benzene ring, but not for benzyl alcohol. I don't know if it's going to be necessary for you to have that name memorized, but I would like you to remember it well enough that when you see it, you're not tricked by that terrible word benzyl, which does not mean what it sounds like it means. Now, of course, there's different types of alcohols, just like there's different types of alkyl halides, just like there's different types of sp3 hybridized carbon atoms in general. So alcohols can be primary, secondary, or tertiary, depending on the carbon that has the OH group directly attached. So I would say that cyclohexanol is secondary because the carbon attached to the OH is secondary in cyclohexanol. Same thing for 2-pentanol. And in benzyl alcohol, this would be a primary alcohol because this carbon is now primary. There is only one methyl alcohol, which you can call methyl alcohol, CH3OH, or we call it methanol. Either name is fine. What would be an example of a tertiary alcohol? Well, I don't know. Let's have some fun here. Maybe something like this compound would certainly be an example of a tertiary alcohol, because now the carbon that bears the OH group is tertiary. And I specifically picked that one because it's not chiral. That carbon is 2 methyl groups on it, so game over. That carbon isn't chiral. What about phenols? Well, phenol itself, again, is hydroxybenzene. Oh, I forgot to name that compound. Let's call that guy 2-methyl-2-butanol. So I think that's the best name for it. Now, phenol itself is hydroxybenzene. And even that name, hydroxybenzene, it's not wrong. You could, in principle, call that hydroxybenzene, but no one does. We call it phenol. So if the phenol ring is substituted elsewhere, like let's say, for instance, we have a nitro group over here, well, we have choices with how to name this one. We could call this either 3-nitrophenol, or we could also call it M, or metanitrophenol. Both names are perfectly fine. They are equally correct. I have no preference for either one of them over the other. And your book does correctly point out that at some point, I don't know if I can draw you a hard, bright line anywhere, but at some point, one has to name the OH group as a substituent. Let me see, especially in cases of benzoic acid and benzaldehyde derivatives. So let's put on a carboxylic acid functional group here. Remember, that's C double bond O, OH. So this compound would, I think, be better named by using benzoic acid as the parent. Remember, benzoic acid was one of those compounds back in chapter 4. That's a benzene derivative that has a common name that's used so much, both the name and the compound itself, that it's worth knowing about. But I would want to say that there's a hydroxy group in the para position compared to the carboxylic acid group. So again, I think one could call this 4-hydroxy benzoic acid. Or if you wanted to, you could certainly call this p-hydroxy benzoic acid. I don't know of a good name, at least a convenient way, to name this as a phenol. It would require calling that carboxylic acid group something really ugly, something I guarantee you much uglier than hydroxy. So at some point it becomes necessary to do that. But again, in OWL, I think you will get some practice doing that. A reminder about hydrogen bonding. We talked about that earlier in chapter 2, so please do review that if you feel the need to. So hydrogen bonding is an intermolecular force that compounds experience if they have either OH or NH bonds. And I guess there's one other. HF also experiences hydrogen bonding, but I feel a little strange saying OH, NH, or FH bonds, because once you form that bond from fluorine to hydrogen, you're done. Both of those atoms can form only one bond. But nonetheless, HF does experience hydrogen bonding. And so alcohols have that in common with water. They have similar intermolecular forces. So that's why smaller alcohols especially tend to be water soluble. And methanol and ethanol are soluble in all proportions with water. So you can make a solution of either methanol or ethanol with water using however much of either of those two with the water that you like. And you will get a solution. It will always be soluble. As those As those alcohols get bigger, as you start getting into propanol and isopropanol and the butanols and the pentanols, as that alkyl group gets larger and larger, of course, then it's getting, then the molecule gets less and less polar overall, and so the solubility will go down. Of course, I would never expect you to memorize any particular solubilities. I wouldn't say, what is the solubility of one pentanol in water in terms of weight percent? No, would never do that. But I would expect you to know that pentanol is certainly less soluble in water than methanol or ethanol, and probably a pretty good guess it's less soluble than propanol or isopropanol also. At least I think that would be a reasonable guess. So hydrogen bonds are generally worth about 20, 30, or 40 kilojoules per mole. Most of your covalent single bonds are in the hundreds, 200, 250, 300 kilojoules per mole. So that's going to result, since we have, so hydrogen bonds are not as strong as covalent bonds, but they still are a substantial force to be reckoned with. And that's why alcohols will have higher boiling points than alkanes of a similar molecular weight, because in order to get the compound to go from the liquid phase into the gas phase, you've got to separate individual molecules of the alcohol away from each other. Remember, in a gas, the gaseous state is much less condensed than the liquid state. So we need to get the molecules to separate from each other and have a lot of space in between them. And if there's this attractive force between the molecules, that's going to be all the harder to do. So, and you can see some examples of this in the textbook. Of course, I don't care if you memorize any particular boiling points. That would be entirely outrageous. But if you check out a few examples, I think you'll be able to satisfy yourselves that this is true. And so just looking at what's coming, maybe let's talk a little bit about acidity and basicity, and then that will probably be a good stopping point. I don't want these videos to get too long. So let's also recall that, that alcohols are amphoteric, like water. In terms of their acidity, pretty low, though there are certainly things that are less acidic. But most aliphatic alcohols are a little bit less acidic than water. Water is a pKa of 16 or thereabouts. And so most aliphatic alcohols have pKa's in the upper teens. So they're usually anywhere from 1/10 to 100th to 1/10 as acidic as water. Phenols are different, though, and I did mention earlier that phenols are special. Phenols are significantly more acidic than aliphatic alcohols. You're trying to erase the board over here, so to speak. So, like I said, other things being equal, if you as similar as phenols and aliphatic alcohols are, leaving as much as you can the same, phenols are going to be about 1 million times more acidic, which means their pKa's tend to be round and about 9 or 10, something like that. So it's a significant difference. And the reason for that is because there's resonance stabilization. Okay, welcome back. Had a bit of chemistry failure here. I think we got it up and running now. So we were discussing how it is that phenol and substituted phenols are a good deal more acidic than aliphatic alcohols. And the reason for that is pretty evident when we look at the conjugate base of phenol, which is this phenolate ion, as it's so called. And the reason we need to think about the conjugate base is because I think you'll agree that this species here is what phenol makes when it acts as an acid, when it gives up H+. In other words, if you take away H+ from phenol, this is what you get. And what we find is that this species is very highly stabilized by resonance. I could come up with at least 3 other resonance forms, which show the negative charge being delocalized and being shared with at least 3 of the carbon atoms on the benzene ring. So the minus charge is not just sitting on the oxygen, it's spread out through the entire benzene ring. And remember, when it comes to negative charge, when it comes to electrons being negatively charged, remember the old idea of like charges repel. And so anything we can do to spread out the minus charge so that it's not concentrated in one area is going to make the species more stable. And that's always going to be the case. And so what this shows is that phenol is rather happy to give up that H+, because when it does so, you get something that's very well stabilized by resonance. Its conjugate base, or the conjugate base of phenol, is well stabilized by resonance, because the minus charge is delocalized. It's not sitting just on the oxygen. It's partly on the oxygen and partly on the benzene ring, delocalized. If you compare that to an alkoxide ion like methoxide, and I could have picked ethoxide or any other alkoxide ion, here the minus charge is localized on that oxygen. So all three lone pairs on that oxygen give it a formal charge of -1, and it's on that oxygen that all of the minus charge sits. Now granted, it's much better to have minus charge in oxygen than on a lot of other atoms. Oxygen is at least quite electronegative, but how much better still to spread out the minus charge like we can in the conjugate base of phenol. So this is why aliphatic alcohols are so much less acidic. It's because their conjugate bases, like which is going to be an alkoxide ion like this, their conjugate bases have the minus charge localized on the oxygen, whereas in the phenolate ion, it's delocalized. And so, this idea that we're going through here can be generalized more fully, and it's an important idea to understand. But the idea is, to put it as simply as I know how, anything you do to stabilize the conjugate base of some acid makes its conjugate acid stronger. And it's, like we said, if the conjugate base is more stable, that makes the acid more willing to give up the proton and turn into the conjugate base. And so anything that destabilizes that conjugate base, anything that makes the conjugate base less stable, is going to make the acid weaker, because now the acid isn't so excited about giving up that proton, so to speak, not to personify these things too much. But so anything that stabilizes the conjugate base makes the conjugate acid stronger. And we have an example here, one that the book gives. I certainly don't expect you to memorize details like this, but if you compare the pKa of ethanol to the pKa of trifluoroethanol, so instead, or I should say 2,2,2 trifluoroethanol to be picky about it. It's just the three hydrogens on the methyl group here change to fluorine. So trifluoroethanol, 2,2,2 trifluoroethanol, is significantly more acidic than regular ethanol. So ethanol is a pKa of, as you see, 15.9, very typical for an aliphatic alcohol. Of course, you do not have to memorize that. Whereas the pKa of trifluoroethanol is 12.4. So it's over 1,000 times more acidic than ethanol. And the reason is that you have these three extremely electronegative fluorine atoms that are sucking the electron density away from the oxygen. Again, think for a moment what we would get here with these two once they give up H+. We can even draw that out probably pretty quickly. Let's see, CH3CH2O minus and CF3CH2O minus. These would be the respective conjugate bases of those two alcohols. And in both cases, we're asking this molecule now to bear this minus charge. And so the conjugate base of trifluoroethanol has a lot of help from these electronegative fluorine atoms that are sucking electron density away from the oxygen. Again, you can consider it to be spreading out the minus charge, so it doesn't have to sit as concentrated in one place. Regular ethanol doesn't have doesn't have that luxury, so to speak. And so that explains why 2,2,2-trifluoroethanol is much happier giving up H plus than ethanol is, to the tune of over 3 orders of magnitude. Remember, the pKa scale is logarithmic. So every notch on the scale, so to speak, is a factor of 10. And so that's why we say trifluoroethanol is over 1,000 times as acidic as ethanol. And of course, I don't care if you memorize all these numbers, but the idea is important. And it's something that we can use to explain acidity in other cases as well, probably in other chapters as well. So what about thiols? Thiols are also more acidic than alcohols. Just so we're always comparing apples to apples, let's consider ethane thiol, CH3, CH2SH. And I don't know the exact pKa value of ethane thiol right off the top of my head, but if I had to guess, it would also probably be roughly about 9, somewhere in that area, give or take. Again, we're talking easily 1,000,000 times more acidic than the corresponding alcohol. And that's because the sulfur atom is much better at stabilizing the minus charge than the oxygen is. True, oxygen is quite electronegative, but sulfur has another advantage. So let's ponder the conjugate base of ethane thiol. You could call that the ethane thiolate ion if you really wanted to, or not. I will not cry if you don't, I promise. But remember that the sulfur atom is much larger than the oxygen atom. So that means we have a much bigger ball, a much larger surface area to spread out the minus charge on when we lose H plus and go to the conjugate base. So that's the main reason why thiols are much more acidic than alcohols, other things being equal. And again, I don't know the exact pKa of ethane thiol, and I would not expect you to either. I would challenge you to look it up. I bet you'll find I'm pretty close. I'm probably within an order of magnitude or something like that. Good. So one last point here is that, like water, alcohols are amphoteric, which means that they can also act as bases. They can give up H plus to give their conjugate base. They can also accept a proton in order to give the conjugate acid of the alcohol, just like water can go from H2O to H3O plus. So alcohols can do the same thing. So if we took, for example, ethanol again, and we added sulfuric acid, even just a little bit of sulfuric acid, what we would find is, to whatever degree we add sulfuric acid, all of that sulfuric acid will dissolve in the ethanol and will protonate the ethanol molecule. And so as a result, it thinks my structures are wrong, but it's wrong, they're right. As a result, what you would wind up getting is the conjugate acid of ethanol, meaning the species that has one more proton than ethanol, and that proton will be on the oxygen. That proton is given up by the sulfuric acid, and so you'll get the conjugate base of sulfuric acid, which is the bisulfate ion, HSO4-. So this type of thing alcohols can also do quite readily, and that's going to become important, I think, in later chapters when we start doing other reactions with alcohols. Other than that, I think that's a very good place for us to end here. We can do the rest of the chapter in another video. So be well, and we'll see you next time.